Greetings, and welcome to a lecture on pointers in C++. Buckle up, it's going to be a bit of a ride. Pointers are sometimes referred to as like the final boss of C++ programming. It's not understanding functions, it's not understanding classes even, or header files. Pointers are really where a lot of people struggle in learning to use C++. And you need to learn pointers because that's kind of the whole reason as to why you want to mess with C++ to begin with, is the extreme flexibility it has in terms of memory management, of being able to look at any location in memory and change where you're looking at easily and so on and so forth. It's one of the main reasons why you put up with this language over other languages that have more intuitive features to them. So we're going to go through this slow. We're going to take this step by step. As you can tell, the code is very commented. And let's get into it. So we're going to start off scrolling down here to main and look at basic declaration for a pointer. So on line 38, we have ye old standard integer, x equals 5. So x is just a standard old integer. Its value is set to 5. Nothing special here. And again, if I am taking a look at, where'd my whiteboard go? There it is. Taking a look at a little memory model here. Oops, forgot to erase a little pointer there. Now, if I'm looking at just, the standard memory model, there's my x, and it's addressing this section of memory right here, and it is 5. And then here, I am declaring an int pointer y. This little asterisk here, the star, is what we use to indicate something as a pointer. And we'll typically read this as int star y. Now, where this goes is not too important. It can be like this, int star space y. It can be int space star space y. Or it can be int space star y. It does not matter. What matters is that the star comes before the variable. That part does matter. You can't put this on the other side of the variable and expect it to work. And then we set it equal to null. Now, if you mouse over null, you will notice that it's actually a define. Null, strictly speaking, is not a keyword in C++. Int is a keyword. It is defined by the language itself and used by the language to mean something specific. Null doesn't technically exist. We define it. Now, that said, practically every distribution of C++ I have ever seen has null defined as 0, like this. But there is syntactically no difference between saying int star y equals null and int star y equals 0. And that's just how you initialize a pointer to mean this isn't pointing at anything. If I flip back over to the memory model, y just simply doesn't exist. It's not pointing to anything. You can't do anything with it at this point. And here is where we are pointing y to x. So again, after this line here, this is where we now have the idea that y is pointing towards this location in memory now. Now, it's very important to have this ampersand here. It's called a reference. A int and an int pointer are different data types. You cannot say y equals x. If I take out this ampersand, I am going to get a red squiggle of doom on my assignment operator. If I mouse over it, value of type int cannot be assigned to an entity of type int star. They are fundamentally different data types. You cannot assign them like that. Because what this pointer is expecting is the pointer is expecting a memory address. Y doesn't want to have its own value, so to speak. Y simply wants to know what location in memory should I be pointing at. So that is what this ampersand here is doing. That is the reference operator, basically. So I'm saying Y equals the address of X. It is the X's reference, not X itself. That makes sense. We are saying this is the memory location that I want. And you can see that in action here with this sequence of couts. I am couting X's reference. In other words, this is going to show me the X's memory location. And I'm going to cout the memory location of what Y is pointing to. This isn't Y's memory location. This is the memory location Y is pointing to. And then finally dereference the pointer, which we'll get back to here in just a sec. Let's go ahead and run this real quick. And as you can see, X's address is this bit of nonsense, and Y's value is the same bit of nonsense. So when I say cout ampersand X, and then I say cout Y after I've done this assignment, they have the same value, which is exactly what we want. We said on line 40, Y should point to X. This is where X is in memory. This is where in memory Y is pointing to. That is precisely what we wanted. So when you are working with a pointer, you generally speaking do not want to work directly with the pointer's value, because the pointer's value is the memory address it's pointing at. And generally speaking, that's not what you want to mess with. Instead, if you want to get to the value of what the pointer is pointing at, you have to do what's called dereferencing the pointer. And we do that with the star operator. And yes, as we'll see when we go back up and look at the functions, that means you can have dereferenced pointers in a multiplication operation for extra confusion. But getting back to the current line of code, line 48 here, the idea is that I want to dereference Y to get the value of what Y is pointing at. So again, coming back over here, if I cout Y, this is what I'm printing out. The whatever memory address it's currently pointing at. If I cout star Y, I am dereferencing the pointer and getting the value of whatever Y is currently pointing at. So when I want a pointer to point at something, I use the ampersand symbol to get a reference most of the time. We'll see an exception to that here in a moment. And when I want to actually use whatever Y is pointing at, I need to dereference it using the star operator again. Now, a pointer can be retargeted at will. So if I have the variable t here, and then I say Y equals ampersand t, well, that's pretty basic stuff. That just simply means, no, I did not want the ruler. Thank you very much. That just simply means that now Y is pointing at t. And again, if I print out the value of Y, again, that's going to be the memory address it's now pointing at. And then if I dereference it, it will be 12. Or at least it should be. And in fact, it is. So we can see that the memory address is different. Instead of 6D4, it is 714 now. So the memory address of where Y is pointing is different. And if I dereference it, it has the value of 12, which is what it should have. Now, what happens if I dereference the variable, or if I dereference the pointer and I change its value, what happens? Well, whatever it's pointing at changes value. So if I dereference y and set it to 20, and then I print out the value of t is going to be 20. If I then take t and change it to 99 and print out the dereferenced y, the dereferenced pointer, it will be 99. Again, we can see that in action here, where t is now 20, even though I changed star y to 20. And y dereferenced is 99, even though I changed t to 99. Because again, remember, these are pointing to the same location in memory. So whatever this is, that's what t is, and that's what y dereferenced is until we point y someplace else. Now arrays get a little bit more interesting with pointers. So we have an array here, int meep. So taking a look back at arrays here for a moment, remember that when I declare an array, let's switch back to code. So I've got int meep equals 1, 2, 3, 4, 5, 6. When I declare meep like this, remember that an array is going to grab a continuous chunk of memory, as I am representing here. It's going to grab this continuous chunk of memory right there. And then meep is referring to the address of where that chunk of memory starts. That is what meep is referring to. And then when I write, or when you write meep of, say, bracket 2, that is saying offset meep by 2 whatever. So we know these are ints, so we know these are 4-byte chunks. So if we say meep of 2, we start here, offset by 2, 1, 2. That would be referring to that section of memory. So how does this interact with pointers? Well, as you can see here, I can just simply say y equals meep. The reason why I can do that is meep is an array, not just a regular integer. I can't say meep equals 5 plus 2. That's an illegal statement. Meep is an array. You can't phrase it like that. I have to, well, technically speaking, we are dereferencing meep by using the square bracket operator. That's how I have to use meep. But since meep is a memory address, again, what meep is pointing to, although it's not a pointer, so let me backpedal on that. What meep is referring to is this first chunk of memory that its array takes up. So the value of meep is this location in memory. And since it's a location in memory, we can just simply say pointer equals start of array. Not a problem. And then if we dereference the pointer using these square brackets, which is completely fine, C++ has no problems with this. So if I say print out y of 3, if we come back here to the whiteboard, by saying y is pointing to meep, I am saying y is pointing to this location. And then if I say y of 3, just like an array, okay, I am pointing here. I am going to offset by 3 ints because, again, y knows that it's an int. So 1, 2, 3. That means y of 3 is pointing here. And sure enough, if we run our code and we look at the first index statement, index 3 is 4, that is precisely what we would have expected to see. We're not going to do anything useful with it, but this is where pointers start becoming fun and confusing. I can do this. So what's going on here? Meep of 1 is dereferencing meep to find the value contained in this memory location. So meep of 1 is an integer value. We come over to the whiteboard. Let's see, let me clean some of these up. So if we say meep of 1, that's saying, okay, I'm starting here because that's where meep's pointing to. I'm going to offset by 1, so I go down here, and so I am pointing to this. So meep of 1 evaluates to the value 2. By putting an ampersand in front of it, I am saying, okay, now give me the memory address of this value. So I know that meep of 1 is referencing this block of memory. By using the reference operator, I am now telling y to point here. And in fact, if I was to, I didn't do this in the code, but if you were to dereference y and just say cout star y, you would get the value 2. But I can still use the square bracket, this operator, to offset my memory location. I can still do this. Which means, if we come back over here, y is currently pointing here. Y square bracket 3 says, take my current memory location, offset it by 3, and give me that value. 1, 2, 3. Y of 3 now points to this, whereas meep of 3 would be here. And again, we can see this in the values when we run the code. No, that's not what I wanted to do. Thank you for being helpful, computer. And now I can't see it because of my camera. Ah! Shenanigans. There we go. Stop doing that. So now index 3 is 5 because, well, as we saw on the whiteboard, it's because y is now pointing to index 1 on the array. So you can do crazy things with arrays, and there actually is a point to doing stuff like that. We're just not quite ready to take a look at that yet. All right. Continuing on. So a little bit of setup here. I'm going to have y point at t, and I'm setting x's value to 1 and dereferencing y and setting that value to 2 to set things up for the functions. So what happens with pointers and functions? Also, a bit of functions that we haven't really talked much about. All right, so version 3 of the functions is a ye old standard function that has 2 integer parameters being passed in. And this function is going to operate exactly how you would expect it to operate. I am passing in x and y by value here. So nothing done inside of this function will impact the code that called it. As far as syntax goes, x is an integer, so you just pass it in as usual. Remember, y is a pointer, so we have to dereference y. I can't, well, one, it wouldn't make any sense just to pass y in, plus you will get a red squiggle of doom complaining about the type mismatch. So you just pass in x, you dereference y, pass in that value, and again, since it's being put in by value, when we print things out after calling the function, nothing has changed. v3, x is 1, y is, which is currently pointing to t, is 2. As expected. I would not have expected values to change there. Let's take a look at version 2, because that's a little bit more interesting. Version 2 is still technically integers, but they are integers being passed by reference. You don't use this declaration syntax outside of functions. Like I would not have down here in main int ampersand z, for example. You only use this format in functions. And a pass by reference is saying, okay, yeah, these are still just regular old integer data types. This is still the integer data type, but when you give me your information, I'm going to grab the address, not the value. And that means anything that I do inside a function that has pass by reference will impact the calling code. Whatever called it, these changes will remain in effect. And we can see that. Yep, sure enough, v2, x is now 6, and y is now 12. X equals 6, y equals x times 2. As far as syntax goes, the exact same for calling it. Again, a pass by reference is still just a standard data type. So pass by an integer, pass by reference, parameter like that, it's still an int. So I still pass in x just like you always do. Nothing has to change there. And I still have to dereference y. Now I can get the same effect as a pass by reference by having pointers. And that's version 1 here. Yes, I did it in reverse order. So now I have 2 pointers. I have an int pointer x and an int pointer y. And that does change how you call it. Now, when I call version 1, x is not a pointer. So I have to grab the reference of x and pass that in. And of course, y is already a pointer, so I can just pass y in, and it will copy the value of the pointer in there. It is worth pointing out, if slightly confusing, that these pointers are being passed in by value. So in other words, if I retarget where the pointer is pointing at inside the function, that will not impact the pointer where the pointer is pointing at back here in the calling code. So that's, just be aware of that. But the values still change. Again, if we run the code, x is now 5 and t is 10 because, well, again, these are pointers. I am passing in a memory location to these two variables, and I'm having to dereference them to assign values and manipulate them. And yes, can be very confusing when you've got multiplication and pointers in the same line. Unfortunately, you just kind of have to deal with it. All right, one last thing to take a look at on the basics of pointers, and that is comparison. Keeping in mind what you are comparing with pointers. All right, so what is our setup here? So I've got two new pointers, P1 and P2. P1 is pointing at X and P2 is pointing at T, and I have set both X and T to have the value of 5. So how does the comparison operators work? Well, in this first one here, it is going to be not equal. Because remember, when I use the pointer without dereferencing the pointer, I am not looking at the value of what it's pointing at. I am looking at what is the memory address this is pointing at. So when you compare two pointers like this, I am asking, are they pointing to the same thing? Which they are clearly not. They are not pointing to the same thing. And so this will come out to be false. Now, if I dereference them, now I'm asking the question, is the value of the thing they are pointing at the same? So P1 and P2 are both pointing to separate areas. They're pointing to X and T respectively. But X and T have the same value, so when I dereference P1 and P2 and compare them, now the comparison comes back as true. Again, if we run this and take a look, sure enough, pointers are equal. Pointers are not equal, and pointers are equal. Just once more reinforcing in the idea that when you're working with pointers, you have to be very careful. Am I working with where the pointer is pointing? Or am I working with the value of what the pointer is pointing at? You always have to keep that in mind when dealing with pointers. Am I manipulating memory? Or am I manipulating where I'm pointing at? Am I manipulating value, or am I manipulating what I'm pointing at? All right, let's talk about the assignment. So this is just a little bit of an introduction to get you used to working with pointers. We'll start taking a look at C strings next week, but for this week, just a little bit of an introduction. So we're going to kind of simulate a deck of cards. So you're going to have an array of 52 elements, just a yield standard array of 52 elements, integer elements with values of 1 to 52. So if I look at index 0, the value will be 1, index 2, the value will be 2, so on and so forth. Standard affair. We've done this before. And then you're going to have 3 int pointers representing a hand of cards. And what you need to do is you need to randomly assign each of those pointers a value from the integer array. And you cannot have 3 of the same card. It's 52 cards, right? You're not allowed to, at least there shouldn't be 2 ace of spades in the deck, right? So after randomly assigning the 3 pointers values from the deck of cards, you need to print them out. So current hand is 8, 16, 28, 10, 42, 49, 12, so on and so forth. And it will keep redealing until you tell it no, and then it'll stop. There can be duplicates between the different iterations here. It's just these three numbers cannot have a duplicate. And yes, the cards, quote unquote, must be pointers. When you are printing out these three values, these values must come from pointers. It's perhaps a little over-engineered for this type of example, but I want to keep the first pointer assignment relatively clean. So, one thing of note to keep in mind, I haven't covered how to do random numbers in C++ yet. You're going to have to research that one. Remember, as a programmer, your biggest skill, more so than being able to memorize language features, is being able to research new aspects of the language that you haven't used yet. And with that, we can get things wrapped up. Good luck with the assignment, and I'll catch you on the next video.